A single announcement from Japan just sent shockwaves through the entire global energy sector, signaling the potential end of the fossil fuel era. In an unprecedented achievement, Japanese scientists sustained a fusion reaction at temperatures hotter than the sun's core. This isn't just another incremental step, it's a quantum leap that has forced world leaders and energy executives to confront a new reality. Let's explore what this breakthrough really means and why the old energy order is panicking. Breaking point. What if we could bottle a star on Earth? In October 2025, Japan's National Institute for Fusion Science, or NIFS, announced a historic milestone at its Large Helical Device. Scientists there sustained a plasma at an astonishing 120 million degrees Celsius for several minutes, a duration that is an eternity in the world of fusion physics. To put that in perspective, the sun's core is a mere 15 million degrees. Led by Professor Masayuki Yokoyama, a leading authority on stellarator plasma physics, the NIFS team used a sophisticated system of AI-driven magnetic fields and advanced superconducting coils to achieve this record stability. This wasn't just a lab curiosity. It was hailed by energy analysts as the closest humanity has come to practical fusion energy. The news, released from Tokyo, spread like wildfire across global news wires, instantly shifting the conversation around fusion from a distant scientific dream to an immediate and disruptive technological force. For the first time, the promise of clean, limitless energy felt tangible, forcing the world to ask a critical question. Did Japan just ignite the beginning of the end for fossil fuels? This achievement demonstrated a level of control that many thought was still decades away. Market panic. Could a scientific paper erase billions from the stock market overnight? The NIF's announcement triggered immediate and severe financial repercussions. Within hours, energy market shares plunged as panic spread through trading floors in Tokyo, London, and New York. The Nikkei Energy Index saw a sharp dip, with major utilities like JERA and Tokyo Electric Power Company losing significant value. Conversely, companies in the nascent fusion sector, like the startup Helical Fusion, saw their stock prices soar by over 20%. Analysts from major financial institutions scrambled to interpret the news, with many framing it as a seismic shift for the energy industry. The bulletin from NIFS was measured but potent, citing the use of AI-driven magnetic confinement to maintain stability. This technical detail convinced investors that this wasn't just hype. The fear of stranded assets, multi-billion-dollar investments in coal, oil, and natural gas infrastructure becoming obsolete, became a stark reality. As clean energy ETFs saw a massive spike in trading volume, the message from investors to the old guard was clear. The financial world was taking fusion energy seriously, and the transition was happening faster than anyone had predicted. Inside the control room. How do you control a substance 7 times hotter than the sun's core? The answer lies in a groundbreaking fusion of human expertise and artificial intelligence. Inside the control room of the Large Helical Device, engineers and physicists, including Professor Yasuhiko Takeri, the Director General of NIFS, monitored a digital twin of the plasma. This advanced AI model, running on supercomputers, processed trillions of data points from thousands of sensors every second. It predicted and neutralized instabilities in milliseconds, a feat impossible for human operators alone. The plasma, a turbulent cloud of charged hydrogen, was held steady not by brute force, but by precise, intelligent adjustments to the magnetic fields. The LHD's massive superconducting coils, cooled to near absolute zero, generated the immense magnetic forces required for confinement. But the real breakthrough was the AI control system that acted as the plasma's shepherd. A system refined over years by diagnostic experts like Professor Kenji Tanaka. When sensors detected a potential collapse, the AI responded instantly, tweaking power inputs and adjusting the magnetic cage. This record-setting run proved that fusion plasma could be managed in real time, transforming it from a wild, untamable force into a controlled and predictable power source. The magnetic bottle. How do you contain something so hot it would vaporize any material it touches? Well, you build a bottle made of invisible forces. At the heart of fusion research are 2 competing designs for this magnetic containment, the tokamak and the stellarator. The tokamak creates a donut-shaped magnetic field to confine the plasma. It relies on inducing a powerful current within the plasma itself to help maintain stability, a feature that, honestly, can also be a source of disruption. The stellarator, the design of the Large Helical Device, takes a different approach. First conceived by the brilliant astrophysicist Lyman Spitzer in 1951, it uses a complex twisted set of external superconducting coils to generate a helical, or spiral-shaped magnetic field. This design doesn't require a large plasma current, making it inherently more stable and capable of longer continuous operation, which is really essential for a future power plant. While tokamaks have historically received more attention, the LHD's success, guided by scientists like Professor Akihide Fujisawa, has shown the immense potential of the stellarator design to overcome some of fusion's biggest stability challenges. It proves that Spitzer's elegant but complex vision is, in fact, a leading contender for the future of energy.
For decades of progress.
This breakthrough didn't happen overnight. Japan's journey into fusion research has been a marathon, not a sprint, fueled by the national imperative for energy independence following the oil shocks of the 1970s. The story begins with early organizational efforts by scientists like the Nobel laureate Hideki Yukawa. A key milestone came in 1985 with the powering up of the JT-60, a large tokamak reactor in Ibaraki Prefecture. For years, researchers at the Japan Atomic Energy Research Institute, under the guidance of physicists like Dr. Masahiro Wakatani, used this machine to push the boundaries of plasma temperature and confinement. In the late 1990s, Japan diversified its approach with the construction of the Large Helical Device. This dual-track strategy of developing both tokamak and stellarator technology proved to be a masterstroke. Collaboration has also been central to Japan's success. The upgraded JT-60SA, which achieved its first plasma in October 2023, is a joint project between Japan and the European Union, serving as a critical support satellite for the massive ITER project in France. This long history of steady investment, global partnership, and relentless scientific inquiry laid the essential groundwork for the recent historic achievement.
Fusion fundamentals.
So, what is nuclear fusion really? At its core, it's the process that powers the sun and every other star in the universe. It involves taking two light atomic nuclei, typically isotopes of hydrogen called deuterium and tritium, and forcing them together under immense heat and pressure until they fuse into a single helium atom. This process releases a tremendous amount of energy according to Einstein's E=mc² equation. To replicate this on Earth, scientists must heat the hydrogen fuel to over 100 million degrees Celsius, creating a plasma. This plasma is confined by powerful magnetic fields, a concept pioneered by physicists like Andrei Sakharov in the 1950s. Unlike nuclear fission, fusion is inherently safe. A meltdown is physically impossible. If the delicate balance of heat and pressure is lost, the reaction simply stops in seconds. The fuel is abundant and clean. Deuterium can be extracted from seawater, and tritium can be bred inside the reactor from lithium, a common light metal. The work of scientists like Professor Katsumi Ida at NFS, who specializes in plasma transport and confinement, has been crucial to demonstrating that these core challenges can be overcome safely and efficiently.
Financial shockwaves.
The ripple effects of the LHD announcement extended far beyond the scientific community, reshaping financial markets in real time. The theoretical risk of fusion disruption suddenly became a tangible threat to the existing energy infrastructure. Utility companies heavily invested in fossil fuels saw their credit default swap rates tick up, a clear sign of growing investor anxiety about their long-term viability. Lobbying firms representing the oil and gas industries ramped up their activities, filing petitions that cited the potential for core industry displacement. Meanwhile, the private sector's confidence in fusion surged. The Japan Fusion Energy Council, or J-Fusion, reported a massive increase in private investment into fusion startups. Companies like Kyoto Fusioneering, led by physicist Taka Nagao, which focus on the practical engineering challenges of building a power plant, like heat exchangers and tritium breeding blankets, saw their valuations skyrocket. Venture capital firms, recognizing the immense potential, began pouring capital not just into reactor development, but into the entire fusion supply chain. The financial landscape was being redrawn, with capital flowing away from the past and toward a fusion-powered future.
Leading the charge.
Japan's fusion success is not just a scientific victory, it's a strategic one, positioning the nation at the forefront of a new global energy paradigm. At the center of this is Professor Masayuki Yokoyama of the National Institute for Fusion Science, whose work has been pivotal to the LHD's achievements. His research really validates that controlled fusion is no longer just a possibility, but an engineering reality. This confidence is now being reflected in national policy. Japan's Ministry of Economy, Trade, and Industry, or MITI, has officially designated the development of prototype fusion reactors as a national priority. The Japan Fusion Energy Council, established in 2024, is actively coordinating efforts between industry and government to create a comprehensive roadmap for grid integration and licensing. Japan's strategy is clear lead not only in the science but also in the commercialization and standardization of fusion energy. The potential for Japanese-developed technologies, like the AI-driven plasma control systems, to become the global standard is now a very real possibility, sparking intense interest and, honestly, some quiet negotiations with international partners seeking to license this groundbreaking technology.
Of government response.
How does a government prepare for a technological revolution? Japan's answer is with a deliberate and forward-thinking national strategy. In April 2023, the government unveiled its Fusion Energy Innovation Strategy, a comprehensive plan to accelerate the commercialization of fusion. This was a clear signal that fusion was moving from pure research into the domain of national industrial policy. The strategy aims to foster collaboration between the public and private sectors, with the goal of having a demonstration fusion power plant operational by the 2030s. This proactive approach, championed by officials like Minister of State for Science and Technology Policy Sane Takaichi, really contrasts sharply with the stances of other nations. Following the LHD breakthrough, METI convened a special working group to assess the disruptive risk of fusion and develop frameworks for a stable energy transition. This includes plans for creating robust supply chains for critical components and fostering a new generation of fusion scientists and engineers, ensuring the nation has the talent to see this vision through. Japan is not just reacting to the future of energy, it is actively building it.
The path forward.
Japan's breakthrough has undeniably accelerated the global timeline for fusion energy, but critical challenges remain on the path to commercialization. The success at the Large Helical Device, a result of decades of dedication from scientists like Professor Osamu Motojima, former Director General of NIFS, has proven the scientific principles. Now the focus shifts to engineering and economics. The next step is scaling this technology from a laboratory experiment to a commercial power plant. This requires developing first-wall materials that can withstand the intense neutron bombardment from the fusion reaction for years on end. It also means engineering efficient systems to extract the heat and convert it into electricity. Global collaboration will be essential. International agreements on licensing and safety standards must be established to ensure a smooth deployment of fusion power. While Japan has taken a decisive lead, the race to build the world's first commercial fusion plant is a global endeavor. The road ahead is complex, but for the first time in history, the destination, clean, safe, and virtually limitless energy, is clearly in sight. Japan's fusion breakthrough is more than just a scientific achievement, it's a pivotal moment in human history. The prospect of a world powered by clean, abundant energy is no longer a distant dream but a tangible goal that is accelerating toward us. The journey is far from over, but the path forward is clearer than ever before, and the implications are, honestly, staggering. What do you think this means for the future of energy and society? Let us know in the comments below. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the technologies shaping our world. Thanks for watching InnoVision Tech.